Welcome students to our new YouTube channel Pharma Tech, the division of excellence. So this is Sunday blockbuster series season 3, and in this we start with the pharmaceutics, that means pharmaceutical technology and modern pharmaceutics. This is the most important section in GPAT exam. So in pharmaceutical technology and modern pharmaceutics there are topics like tablets, capsule, emulsion, suspension, aerosols. But we start with the some basic chapters of the pharmaceutical technology. That means the basic of this pharmaceutical technology. And the first is the pre-formulation. And if you don't understand this pre-formulation, then the next chapters of tablets, emulsion, capsules and suspensions, you don't understand the formulation studies and formulations, that means how to make this tablet, capsule, aerosol, suspension studies. So let's start to this chapter, pre-formulation. So this is the basic chapter of pharmaceutical technology. So this pre-formulation is a link between the drug discovery and the drug development studies, and it is the fundamental step in the rational development of dosage form. And this pre-formulation, it can also be defined as an investigation of physical and chemical properties of drug substances alone and when combined with the patients. And next we see the goals of this pre-formulation. The goals is to formulate an elegant, safe, efficacious dosage form with good bioavailability, and also to formulate the new dosage form of an already existing drug, and also the to determination of all the properties of drug and the best suitable dosage form for the drug molecule. So next we see the some physical characteristics of the in pre-formulation. The first one is bulk characteristics. The bulk characteristics include the particle size and surface area, crystallinity, that means crystallinity, flow properties and bulk density, drug excipient compactability, osmolarity, wettability, polymorphism, hygroscopicity, compressibility, electrostatic charge and rheology. These are the bulk characteristics. So next we see the some solubility analysis. In solubility analysis there is aqueous solubility, in that intrinsic solubility and dissociation constant. And next one is partition coefficient, and also the Common effect and solubilization and thermal effect and dissolution. These are the in solubility analysis. So next we see the stability analysis. In that solid state stability, the solid state stability and solution state stability. So in stability analysis these are most important: solid state stability and solution state stability. So next we see the chemical characteristics, and they includes oxidation, hydrolysis, photolysis, racemization, that means racemic mixture, and polymerization, isomerization and decarboxylation and enzyme decomposition. So next we see the polymorphism. So this polymorphism, it is the ability of any compound or element to crystallize as one or more distinct crystal species with different internal lattice. And the examples of polymorphisms are carbon, in cubic diamond and in hexagonal graphite. So as per class wise and the percent of polymorphism, we see the first class is barbiturate and percent of polymorphism is 63%, and in steroids 67% of polymorphism is shown, and in sulfonamides 40% of polymorphism is shown. And the effect of polymorphism on bioavailability is the most important consequence for the drug substances if the bioavailability is mediated via dissolution, and the oldest known example is chloramphenicol palmitate. So next we see the types of these polymorphism. In that the first one is phase transition, the process of transformation of one polymorph into another, which may also occur on storage or during processing. In is called as phase transition process. In that, the first one is enantiometric polymorphs. These enantiotropic or enantiotropic, those words suitable you say, enantiotropic polymers. So these enantiotropic polymers is a phase transition is reversible, that means metastable stable, example is sulfur. And in monotropic polymers, phase transition occurs only in one direction, metastable stable, example glyceryl stearate. So in enantiotropic polymers, phase transition is reversible, that means metastable, and example is sulfur. And in monotropic polymers, phase transition occurs only in one direction, that means straight forward, and the example is glyceryl stearate. So next we see the solvates, pseudopolymorphism. So the solvates pseudopolymorphism. So the solvates are molecules, complexes that have incorporated the crystallizing solvent molecules in their specific lattice position and in a fixed stoichiochemistry, that means in fixed stoichiometry. When the solvent incorporated in the solvent is water and it is called as a hydrate. That means when the solvent incorporated in the solvent is water, it is called as a hydrate. So a classical method for distinguishing these solvates from the polymorphs involves the observation of the melting behaviors of crystals embedded in silicon oil, where upon heating bubbles of solvents are generated by solvates, and in cases of polymorphs no such generation occurs. So next we see the methods to identify the polymorphism, and the methods like the optimal crystallography and also the hot stage microscopy. In hot stage microscopy, using this technique of hot stage microscopy, the fluid phase transformation as a function of temperature is observed. Generally, silicon oil hot stage microscopy is used for the detection of pseudopolymorphism. So in the GPAT there is a question, which oil in hot stage microscopy is used for the detection of pseudopolymorphs, and the right answer is silicon oil. And the X-ray diffraction method using Bragg's equation, n lambda is equal to 2d sin theta, where d is the distance for different planes of crystal, lambda is the wavelength of X-ray used, and theta is the angle of incoming beam, and n is the order of spectrum. And in X-ray diffraction, the powder X-ray diffraction gives the basically focusing on packaging pattern of the atom, and it exact relative the location of atom in crystal is determined. And in NMR technique, in this NMR technique, the powder sample must be rotated at a special angle with respect to the magnetic field. And next we see the FTIR technique, that means Fourier transform infrared spectroscopy technique. In this FTIR technique, it has been used to quantify the binary mixture of the polymorphs. So next is dilatometry. So this dilatometry is the measures the charge in the volume caused by the thermal or chemical effects. The next is the microcalorimetry. So this microcalorimetry is used to characterize the thermodynamic properties of the different molecules. So next we see the thermal methods. In thermal methods like differential scanning calorimetry and differential thermal analysis are the thermal methods used, and also the thermal gravimetric analysis is used, and also the last is melting point determination. So these are the methods. So next we see the properties of polymorphs. The properties of polymorphs are the polymorphs shows the same properties in liquids or in gaseous state, but they behave differently in the solid state, and the polymorphs differ from each other with respect to the physical properties like melting and sublimation temperature, vapor pressure, solubility and dissociation rate, stability, optical and electrical properties, and crystal habit. So and also the hygroscopicity, heat capacity, solid state reactions, compression characteristics and conductivity. So these are the properties of polymers. And these properties polymers differ from each other with respect to these all physical properties. So next we see the crystal. A crystal is a solid in which the constituent atoms or molecules or ions are packed in a regularly ordered repeating pattern extending in all three spatial dimensions. Next we see the classification of chemical compounds. The chemical compounds in two class, habits and internal structure. The internal structure in two class, crystalline or amorphous, and in crystalline it shows single initiative, and that means single entity and molecular adducts, and the single entity forms the polymers and the molecular adducts forms the non-stoichiometric inclusions and stoichiometric solvents, that means hydrates, and the non-stoichiometric inclusions like channel, layer and clathrates, that means cage. These are the classification of chemical compounds. So in that we first see the amorphous compounds. So these amorphous forms are usually of higher thermodynamic energy than the corresponding crystalline forms, so solubilities as well as dissolution rates are generally greater, but due to the higher energy they are unstable and tend to revert back to a stable form. This is particularly true for the formulations like aqueous suspensions. In the cases of amorphous Nohobiacon suspension, in Nohobiacon suspension it slowly converts to a crystalline form and thus becomes less and less absorbable and finally loses the therapeutic effects. Thus, a search for additives was begun to prevent such conditions. So next we see the characterization of these amorphous solids. The only positive way to differentiate amorphous forms crystalline solids is by means of X-ray powder diffraction. This technique gives very diffuse reflections of amorphous. This technique gives very diffuse reflections of the amorphous compounds where the d is the distance and the distance between parallel lines, that means the distance between parallel planes in which the atoms of the crystalline cannot be determined as in done with the crystalline solids. Then next we see the clathrates. So the clathrates is a single phase solid with two distinct components. The clathrate is a single phase solid with two distinct components, the host and the guest. The guest is retained in the closed cavities provided by the crystalline structure of the host. Thus, it is non-stoichiometric molecular adducts, and the major class of clathrates are hydroquinone clathrates, water clathrates and phenol clathrates, etc. So next we see the pharmaceutical applications of these clathrates, and the applications of clathrates include in purification. In purification of benzene was purified of one of its usual contaminants, thiophene, by clathrate formation, although the both form clathrates with monoamine nickel cyanide. Benzene is more firmly held in a cage structure, so it is preferentially clathrated and separated from the solution by filtration. So the next application of clathrate is the separation of rare gases. So in the separation of rare gases, the argon gas is separated from neon by adjusting the pressure conditions in which the hydroquinone argon clathrate is formed, while neon does not form the clathrates. And the next application is separation of optical isomers. In that, the inclusions complexing substances that will separate optical isomers is triothiamotide. So next application is the storage of the inert gases. They are used for the convenient storage of inert gases like hydroquinone or to introduce such gases into fairly inaccessible locations. The gas can be released by heating or dissolving the clathrates. So next application is mode of action of anesthetics. In non-hydrogen bondings, anesthetics work primarily due to the clathrate formation of molecules of anesthetic agents with water contained in the neurons and around the neural network. So next we see the comparison of crystalline and amorphous forms. The amorphous forms are least ductile, that means highest in detention hardness value, and in crystalline form these crystalline forms are more ductile, that means in low indentation hardness value, and in amorphous forms highest indentation hardness value, and amorphous forms are less ductile and crystalline forms are more ductile. And in amorphous forms compacts with lowest tensile strength, and the crystalline forms compacts with highest tensile strength. And the amorphous forms compacts have high brittleness value, and the crystalline form compacts have low brittleness value. And the amorphous forms requires a low compression stress to form a compacts, and crystalline forms requires a higher compression stress. And the amorphous forms are randomly arranged molecules, and the crystalline forms are fixed molecular order. And the amorphous forms have no melting points, and in crystalline forms they have a distinct melting point. And the amorphous forms isotropicity, that means properties are same in all directions. So amorphous forms shows the properties are same in all directions, and in crystalline form the anisotropy, that means their properties are not same in all directions except the cubic crystal. So next we see the comparison of solubility of crystal solvates and hydrates. Amorphous form is always more soluble than a corresponding crystalline form. The dissolution rates of hydrates are less than corresponding anhydrous crystalline forms. Examples are glutathamide and theophylline, caffeine, succinyl, sulfathiazole and phenobarbital. And the dissolution rates of the organic solvates are higher than the corresponding pure crystalline forms, and the examples are 1,4-dioxane solvates of nifedipine shows the better solubility than dihydrate form. So the next we see the importance of crystallinity in pre-formulation studies. This is most important for your GPAT and your basic studies. So the importance of crystallinity in pre-formulation studies, in that we first see the effect of solubility and bioavailability. In that the antibiotic nohobiocin is essentially inactive when administered in crystalline form. The antibiotic nohobiocin is essentially inactive when administered in a crystalline form, but an anhydrous form, the absorption of gastrointestinal tract, that means GIT, proceeds rapidly with the good therapeutic response. Thus, due to the difference in solubility, amorphous nohobiocin is 10 times more bioavailable. And the hormone insulin presents another striking example of different degree of activity that may result from use of different physical forms of it. And the insulin is a protein that forms an extremely insoluble zinc-insulin complex when combined with zinc in presence of acetate buffer, and depending upon the pH of acetate buffer solution, and the complex may be an amorphous, precipitate or crystalline material. So next we see the types of insulin and forms of insulin and one set of action and duration of action. So the first type of insulin is prompt insulin zinc suspension. This is called as semi-lente, and the form of insulin is amorphous, and one set of action of this semi-lente insulin is fast and duration of action is short. So the next is extended insulin zinc suspension. This is called as ultra lente, and the form of insulin is crystalline, and the one set of action of this ultra lente is slow and duration of action is long acting. because this is ultra, that means long. So next is last is insulin zinc suspension, lente, and the form of insulin is lente is 30% amorphous plus 70% is crystalline. So this is mixed form. So next we see the one set of action of this lente is fast and duration of action is intermediate in lente. And the more soluble form of chloramphenicol palmitate, form B, shows the greater bioavailability after oral administration than least soluble form A. And the similarly in chlorotetracycline hydrochloride, form is more soluble and bioavailable than corresponding alpha form. Then next we see the chemical stability. In other instances, crystalline forms of drug may be used because of greater stability than corresponding amorphous forms. And the examples of chemical stabilities are crystalline forms of penicillin G as potassium or sodium salt are more stable. And the chemical stability examples are crystalline forms of penicillin G as potassium or sodium salt are more stable in chemical stability. So next, at last, we see the solubility analysis. In that we first see the aqueous stability. The aqueous stability, a drug must possess the aqueous solubility for therapeutic efficacy in physiological pH range of 1 to 8 at 37 degrees Celsius, and the poor solubility less than 10 mg per ml may result into bioabsorption problems. And if the solubility of drug is less than 1 milligram per ml, it indicates that need for a salt, particularly if the drug will be formulated as a tablet or capsule. And in the range of 1 to 10 mg per ml, the serious consideration should be given to salt formation. And there are two fundamental properties of mandatory for a new compound. The first one is intrinsic solubility and second one is ionization constant. The intrinsic solubility is the solubility of weak acidic and weakly basic drugs as a function of pH can be predicted with the help of equation S is equal to Sn in bracket 1 plus K1 upon H plus, so for weak acids, and Sn Sb in bracket 1 plus in bracket H plus upon K2. This is for weak bases where S is the solubility at given pH, S alpha is the intrinsic solubility of the neutral forms. K1 is the dissociation constant of weak acid and K2 is the dissociation constant of weak bases. And the intrinsic solubility should ideally be measured at two temperatures. That means first temperature is 4 degrees Celsius is to ensure that physical and chemical stability, and 37 degrees Celsius is to support the biopharmaceutical evaluations. So next we see the methods to determine the solubility, and the methods are first equilibrium solubility method. In that an excess of drug is placed in a solvent and shaken at constant temperature over a prolonged time, that means up to 24 to 72 hours, that means whole 1 or 2 days, that means 1 or in 3 days, and till equilibrium is attained. So shake at constant temperature over a prolonged time of 1 to 3 days till equilibrium is attained, and after this the filtration is done, and after that analyze the supernatant via the HPLC to determine the degree of solubility. So the HPLC we see in the pharmaceutical analysis. High pressure liquid chromatography, that or high performance liquid chromatography, and also second method is turbidometric solubility method, and third one is nephalometric solubility method, and also the fourth one is ultrafiltration LC or MS solubility method, that means, and also fifth one is direct solubility method. These are the methods to determine the solubility. Then next at last we see the ionization constant pKa. This ionization constant is the unionized forms are more lipid soluble than more rapidly absorbed from gastrointestinal tract, that means GIT, and the relative concentration of unionized and ionized form of weakly acidic or basic drug in a solution at a given pH can be calculated using the Henderson-Hesse-Blach equation. This Henderson-Hesse-Blach equation is the most important for GPAT, and the equation is pH is equal to pKa plus log of unionized form upon ionized form minus weak bases, and also pH is equal to pKa plus log of ionized form upon unionized form minus weak acids. And next are the uses of these equations is to determine the pK value and also to predict the solubility at any pH provided that C0 and the pK are known, and also to facilitate the selection of suitable salt forming compounds, and it predicts the solubility and also the pH properties of the salts. And at last we see the limitations of this method is to fail outside the pH limits of 4 to 10 or when the solution is very dilute. These are the limitations of these equations. And next we see the last methods to determine the pKa value, and the methods for determining the pK values are potentiometric method, conductivity method, dissolution rate method, and liquid-liquid partition method, and spectrophotometric method. These are the most important methods for determining the pKa value: potentiometric method, conductivity method, dissolution rate method, liquid-liquid partition method, and spectrophotometric method. And note that 75% of all drugs are weak bases and 25% are weak acids, and only 5% are non-ionic amphoterics. So in this way we complete this topic pre-formulation part 1. So we continue this chapter in short in part 2, next part 2. So please like, share and subscribe to our channel, and hope you like this video. Please, if you like this video, please comment on comment section, and please share this video to more and more to your GPAT aspirants and CET aspirants too. And also stay connected with our channel Pharma Extech. And thanks for watching. Thank you for watching. Stay tuned and stay connected with Pharma Extech. Thank you. Welcome students to our new YouTube channel Pharma